In this video tutorial, I'm trying to show how a very simple implicit dynamics problem can be solved. Uh, and essentially, it's trying to kill a fly with a cannon because this is such a simple problem that doesn't require a sophisticated finite element code to do that. But the idea is that if one cannot do a simple problem, it's very unlikely that when the problem becomes complicated, uh, we can actually solve it, or even at least solve it properly. Okay, so let's look at this problem. It's a mass spring damper system, and the mass is assumed to be rigid. And what we do is we displace this mass a certain amount and give it an initial velocity and release it. Okay, so basically it begins going back and forth, and because it's a damping problem, eventually the vibrations die down. And this this video is part of the series that I'm doing for people who are are familiar with the Abacus CAE program, and they probably want to either switch or at least do it in parallel because the solver in the 3D experience release 2023X is actually the Abacus program. Okay, now, what I usually do is I select the problems that are done by other people using the CAE so that one can actually watch those, the Abacus user can watch those, and then follow my tutorial in order to see what the changes are between the two software. It is true that the solver in 3D Experience is the Abacus program. However, the interface is completely different, and the functionalities in some cases are different. So this particular problem was actually taken by this YouTuber, and it is done by her uh, using the Abacus CAE. So what I'm doing is replicate what was done in that tutorial and show how it works for the 3D experience. Now, it's a problem that actually can be solved analytically. So the solution to this damped vibration, free vibration problem is right here, where all the parameters that you need are known, and the values are given there, and the initial conditions are zero 0.1 meter. So you move this mass by 0.1 meter in a static step, and then we release it. But when we release it, we also give it an initial velocity of 0.01 meters per second. So here's the analytical solution. And if this is done, uh, you end up with a curve like that. Although these dimensions, this is in millimeters, and this is in second. Okay, so let's go ahead and do the problem. Uh, we go to 3D Experience right there. Let's start with the part file. Our geometry is very simple. Actually, it's just 2 points, pretty much it, because we solve this thing as a single degree of freedom. All right, so I'm going to create 2 points because it is not necessary actually to display the spring. It is all you need is to say that spring starts at that point and is connected to the ground, and here's the stiffness. But personally, I like to see the spring. So we're going to create 2 points. One is at the global origin here, and another one which is 20 millimeters away on the y-axis. So 20 millimeters away on the y-axis. So these are the two ends of my spring. Okay, this is it. This is pretty much the geometry. So now we're going to go to the structural model creation, and under standard finite element mesh, there is no mesh here really, but you have to go through these steps. And this just accept the default. All right, so if you click on the abstraction tab here, see that the abstraction tab, there is a point mass here, or point inertia, point mass. You click on it. Well, it says, where do you want to put it? I want to put it on that point because I want to be able to see things. So it's 2 kilograms. The mass is 2 kilograms. Okay. And then if you click on the connections tab right there, see that? To the right, The third one from the right-hand side, you can select rigid connection or a spring connection. That's what I want. You click on it. Now you can do it between a point and the ground, or you can do it between 2 points. I'd rather do it between the 2 points. So there's going to be my point number one. And for the ground, I'm going to, or actually not the ground, instead of the ground, I will select this other point, which I created here, there. And if you zoom in, you can actually see that there is a something that looks like a spring is drawn, but that's really for visual purposes only. It is a linear axial spring, and the stiffness of it is 4. Yeah, the stiffness of it is 4. Notice that here it was given as 4 Newton per meter. Now, I can define the damper right here as a part of a combination of spring and damper, but to do that is you have to click on the Enable Advanced Behaviors, and you click on the pencil here to edit. Ordinarily, when you see something like that in 3D Experience, you can go and select these boxes and it opens up. But here, unfortunately, the boxes don't open up. You just have to select the text next to it. So damping, you click on the damping here. Notice it opens up. It says along the X direction, but this is the local X direction, along the axis of the spring. So it doesn't matter that I put it here on the Y. It just doesn't matter. You select it. And for the damping value, I believe it was 1. Is the 1? Let me see. Yeah, damping value is 1 in that unit. And that's pretty much it. Okay, so there are some options here, linear, non-linear. Ours is a linear damper, and we say okay. That's pretty much it. Okay, now we're going to go to, instead of structural scenario creation, I will go to mechanical scenario creation because there's a lot more here that you can do that possibly may not be possible in the structural scenario creation that I've been doing many tutorials with it. But all, everything that you could do here is also buried there plus more. You click on it, wait for the thing to pop up. Now, I will change this to the structural analysis type because if you make it general, it still works, except that there will be some icons there asking for temperature and flux and things like that, that we don't have it in the present problem. So I changed structure, only things related to structure is going to show up. And then you have to create your finite element model. We just created a finite element model, which is just basically a mass and a spring essentially, but you have to select. Okay, good. Now, what I'm going to do is I'm going to restrain this point so that it is pinned on the ground. So you click on, let me actually, the first step that we're going to do, although I can apply the conditions here, boundary conditions actually, but the problem is that everything is dimmed here. So you select your step on the procedures tab. First you do a static step, okay? And I'm pretty sure you can do linear perturbation, static perturbation step 2, but I rather use static step. I select the advanced tab here, uncheck the geometric nonlinearity. This is a static problem, so this is a dummy time. It really doesn't matter. We just leave it the way it is. All I did was to uncheck the geometric nonlinearity, but so it's okay. Now you can go and on the boundary condition, notice that now these are not dim anymore. So let's select the fixed displacement. So this point is pinned X, Y, Z. Here rotations are totally irrelevant because this is a linear spring, translational spring. So whether you check these or uncheck it, it really doesn't matter. So that's the first restraint. And then another one at this end. Okay, now remember, because there is no force acting in any direction, even if you don't put this restraint, in all likelihood it will work, but I rather, because it's moving along this axis, I rather do it properly. So X and Z, and then say OK. And now, this is the static step that is being created here. See that static step being created here? And of course, these restraints that I put in there, it also appears in the restraints branch up here. You can see that. Now, I want to take this and in the first step, move it by 0.1 meter. I move it for 0.1 meter, and in the second step, I just released it. So right now, we're in the first step. So you go here, under apply translation, you select that point. If you're having a hard time picking it, zoom in there. In the direction Y, by the amount 0.1 meters, which is 100 millimeters, because the unit here is millimeter. Or you can type 0.1 meter, it's going to convert it, unless you go and change the units in in your menu. Okay, that's pretty much it. Okay, this is going to be for step 1, just the displacing of that. Now, I can run it, but there's really not much I can see. It's just at this point it's going to move. Okay, I want it to move. So let me instead go and procedure insert my explicit, or not explicit, implicit dynamic step. I want to do it over a 20-second interval, because these graphs that I showed you, I've done it over 20 seconds. Okay, good. Now, for the maximum number of steps, I put down 1,000. We don't need that much. For the initial step, I put down 0.01. This is the minimum step. And for the maximum step, I'll put down also I'll put down 0.1. How about that? Good. That's pretty much it. Oh, let me take the geometric, even here, I'm going to take the geometric nonlinearity out. So under advanced, I uncheck this. Now notice that the implicit dynamics has been created here. Yeah, and these things, these two restraints, which were put in the static step, have been automatically, including the translation, has been automatically uh, transferred to or propagated, as Abacus CAE people would like to say, propagated. Now, a couple of things. If you right click and say manager, feature manager, first of all, there's red here. Okay, no problem. So cancel that. Let's update everything. Okay. Right click, feature manager. Okay, good. So here's a step 1 static step. Here is implicit dynamics. But notice that that translation has been propagated. I don't want it. In Abacus CAE, you just go and deactivate this. But the problem is that if I deactivate it, it's also going to disappear from the static step. Let me show you. So deactivate. Notice that it also disappears from this. I can either undo or activate it back to active. So I don't want to actually deactivate. Okay. So I'm going to close this, put the cursor on this translation here. See that? Right click, remove apply translation in the implicit dynamic step. Deactivating, unfortunately, it also removes it from this step. So deactivate. These I wanted to stay. And then I want to give it in this step, I want to give it an initial velocity. Now notice that under the boundary condition, there is something called applied translation of velocity. This is not it. This is not it. You go under initial conditions, that's what you want, initial velocity. You click on it, and you have to select this point. If you're having a hard time, just zoom in. If you're still having a hard time, hide some of the stuff, hide this stuff, there. In the direction Y, by the amount 0.01 meters per second, which is 10 millimeters per second, right? Good. That's pretty much it. Okay. Now these are the things I hit them. If you want, you can get them back, although it really doesn't do much. So yeah, if you prefer, you can have them back. Now, that's pretty much it. So you go to simulate. Now you have to ask for data. For example, uh, I want this point, the position of this point, translation of this point, and velocity of this point to be plotted if needed. I will need it. So I click on this output while I'm in simulate. Before you simulate run it, you click on the output and go ask for the stuff. First of all, I want the history output and I want that point. So let's see if we can get that point. I'm going to hide this there. It's kind of hard to pick it. Now you want the let's see, you want the translation, and only translation in direction 2 is needed. And if you want velocity 2, here's the velocity, and only velocity in the direction 2. Say OK. And it was every step. So that's pretty much it. Let us actually save this. File, save, and we go and first of all do a model and scenario check to see if there are any obvious errors that we need to fix. Nothing there. We do a simulation check. If there are any inconsistencies in the kind of thing that we asked for, it's going to reveal it, may reveal it. I'm pretty sure this is going to be okay. There may be some warning messages. That's a good idea to read these, but after a while you become complacent, and let's actually check and see what this is saying. Yeah, it says there's some data that you're asking that is not available, probably because I asked for that information, and there's the static step. That information is totally irrelevant. There is no time history analysis in the static case. But so maybe that's what these things are. You close it, and finally we run it, and this is where we actually want to see the time history analysis of the motion of that point. A very simple problem. That's why I called it killing a fly with a cannon. But if this was a very complicated three-dimensional problem, the same approach would work. And I will do some videos for things of that nature. You want to be able to see the color, the deflection, contours, and things like that, which you cannot do it for a single degree of freedom system. Going very fast, you can see this. Extracting the results. There were some warnings. I'm pretty sure these warnings were the same type of warnings that we had before, that some information does not apply in the static step. Okay, good. So let me close this. There is really not much you can see because this is a single point. I mean, you don't have any color to show you. What we can do is to go to the history plot. See that? XY plot from history. Let's get a plot of the translation. There is a translation in the direction 2, because that's all I asked for, by the way, and over versus time. So just say apply, and there we are. And this is that. If you want to see the velocity, notice that it starts at this history plot starts at deflection of 100 millimeter, as I was expecting. I remember I stretched the spring to 100 millimeter and then let it go in the second step. So that's what happened. You want to see the velocity, you can change this thing to the velocity better be 10 millimeters per second. So let's go and select the velocity right there, and component 2, and apply, and OK. And notice that although this is in meters per second, if you zoom in, so let's zoom in. Let me zoom in here. it is 0.01 meters per second, which is exactly what I have. So there we are. We solved this problem. There are a few other tutorials that I have prepared for this one specific problem that are posted on YouTube also. I'll do a few more related to the same YouTuber, the work that the YouTuber has done, and its implementation in uh, uh, release 2023X of 3D experience. Now, remember, the reason I emphasize 2023 is because this is a fast evolving code. They're making a lot of changes, and therefore, if you go to earlier version or later version, there may be some minor or some changes in the interface and how dialog boxes look like. Good luck.